So we now have all the ingredients to build our many-body Hamiltonian. We have our non-relativistic Lagrangian for bosons with a contact interaction. We have the mode expansion in a box for our field operator. And we have its canonical momentum conjugate. The expression for the Hamiltonian was given to us by Noether's theorem. For a time translational invariant Lagrangian like this one, the conserved charge is the energy, which is given by the Hamiltonian. Note that in doing this, there is an ambiguity in writing the interaction term, in particular the A daggers and the A. In principle, they could be written in any order. We could start with the A and have the A dagger, or A dagger A, A dagger A. But it turns out that the only order which gives at the end a meaningful interaction is what we call the normal order. So the normal ordering is the action of putting the A daggers on the left and the A's on the right. To convince yourself, have a look at Lancaster and Blundell in chapter 4.4, where they try a different order and show that it leads to spurious terms. Because our fermions are now in a box, the equivalent of the Dirac function is now given by a Kronecker delta. Using this property, we see that we can rewrite the kinetic energy term, while the interaction term becomes, which we can rewrite by shifting k into q plus k. The kinetic energy term is a one-body operator because it has only a sum over A dagger A. Indeed, we see that it annihilates a particle with momentum p and then it recreates it. So this operator just counts the number of particles which have momentum p, and each of them contribute to the usual p squared on 2m. The interaction term, however, is a two-body operator because it has a dagger A form. We see that it annihilates two particles with momenta p and q, and then it recreates two other particles with momentum p minus k and q plus k. So of course the total momentum is conserved. So what the operator does is that it counts the number of pairs of particles which have the right momenta and then make them contribute an interaction of g onto v. So this is a specific interaction which corresponds in coordinate space to a delta interaction, to a contact interaction. And that's because we assume the mass of the mediator to be extremely heavy. If we, however, kept some higher order in the inverse of the mass of the propagator, we will have obtained an interaction which will have a finite range and some function of the distance between the particles. Finding the eigenstates of such a Hamiltonian is usually a difficult, if not impossible task, and that's because of the two-body nature of the interaction. So we need to introduce usually approximations, and a common one is called the mean field approximation, in which the two-body interaction is approximated by a self-consistent one-body potential.